In this section of chapter 3, we'll discuss about alkenes with E or Z stereochemistry. First, we're going to explain to you why we need to have E or Z designation and why cis trans is not sufficient. In last section of chapter 3, we gave you an idea about the cases in which cis or trans doesn't work. Now, if you look at this molecule, you can see here there's the ethyl group. This is the ethyl group, and this is the methyl group. Now, if there is no other group in this case, then this would be clearly a cis isomer. So let me write down that. So if I have a double bond, C double bond C with ethyl group, C is the ethyl group, hydrogen. So let's highlight this. And the methyl group, C, and say you have a hydrogen. So this is clearly a cis isomer or cis stereochemistry. We often use the word stereochemistry because stereochemistry talks about how different groups are organized. Now, if I replace this hydrogen by Br, which is in this compound, we can no longer call it a cis or trans, because if you think about the CC group and Br, you would call it trans. On the other hand, these CC and C are in cis position. So that's why you cannot unambiguously label this as a cis or trans isomer. So we obviously see that we need to have another type of designation, which could be E or Z. In order to determine E or Z stereochemistry, we apply Kahn-Ingold-Prelog rules. In order to apply the rule, you need to select carbon-carbon double bond and examine atoms directly attached to these carbon-carbon atoms. So for example, if this is the double bond, and you need to look at what is bonded here, 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 and here. So an atom with a higher atomic number gets the higher priority than an atom with a lower atomic number. So for example, if I have Br in here, so this is Br, and so at the bottom I have Cl. Obviously Br has a higher priority because its atomic number is 35, so its atomic number of Br is 35, and atomic number of Cl is 17. So this is the higher priority. Let's have H there for high priority, and L is for low priority. In the same way, you're going to do the same thing on the right hand side before you designate E or Z stereoisomer. Now this is an example. I'm going to show you how we come up with E or Z. Let's begin with the bottom one. Again, you're focusing on this carbon-carbon double bond and split that into two halves like this. Now first focus on the left hand side. What is bonded directly to this carbon? Obviously on one side you have hydrogen, which has a low priority, atomic number only 1. And with this carbon is the methyl group. Methyl group, keep in mind the bonding is through carbon, carbon and carbon. So obviously carbon has a higher atomic number than hydrogen, so it gets a higher priority. So I'm going to write down H for higher priority. And since I have hydrogen, so it gets the lower priority, I'll write down L. On the right hand side of this carbon-carbon double bond, we have Cl with higher atomic number, so I'd call it H for getting high priority. And CH3, again, the bonding is through carbon. So carbon has the lower atomic number, so it gets a lower priority. Now, if two highs or two lows are on the same side, we call it Z. Z. So in this particular case, we name this compound as Z2-chloro because this is 1, this is 2, this is 3, this carbon is 4. So Z2-chloro, because in the second position you have chloro, this is the chloro, and then there are 4 carbon longest chain, so that's butene, and the functional group is in second position, so that's why Z2-chloro-but-2-ene. So this is the right name of this compound, or we can just say Z2-chloro-2-butene. Now how do I remember this? Z for same side. It's like somebody has an accent and can't pronounce same. So keep that in mind. If two highs or two lows are on the same side, we'd call it a Z. And if they're on opposite side, we'll call it an E. Now let's focus on the upper molecule. I can split that into two halves. Now here I have only hydrogen. Atomic number is only 1. Here we have carbon-carbon bond between methyl and this carbon. So the bonding is really through this carbon. And carbon has the higher atomic number, so it gets the higher priority. Hydrogen gets the lower priority. On the right-hand side of that molecule, again, I have Cl, which is a higher atomic number, so get a high priority. And carbon has the lower atomic number, so get a lower priority. Now let's see here, high, high, they're in opposite side. So that's why it's E. So E2-chloro, again, this is in naming compound, you have to get the longest chain containing the carbon-carbon double bond. Of course, you not only have to give lowest number to the double bond, also substitution group Cl will have to get the lowest possible number. So that's why we get, this is going to get 2, this is going to get 1, this is 3, and this is 4 in the longest chain. So E, because they're on opposite side, E2-chloro-2-butene, or E2-chloro-but-2-ene. Often you can't make a decision based on the first atom that is directly bonded to carbon-carbon double bond. Like in this case. This is directly bonded to carbon here. This is also directly bonded to this carbon here. That means I can't make a decision about priority based on these bonded atoms. So the rule is, if you can't make a decision, then you need to look for second, third, or fourth atoms until the first difference is found. Like in this case, let's split this molecule into half. Why I'm saying that this is the high priority? The reason is this is bonded to carbon, this is also bonded to carbon. So I need to go for the next bonded atom with higher atomic number. This is bonded to a carbon that has a higher atomic number than hydrogens that's bonded to this other end. So that's why this group has the higher priority and this has the lower priority. Sequence rule for priorities tells us that multiple bonds are considered to be equivalent to the same number of single bonded atoms. Like in this case, C double bond O would be treated as if there are two oxygen bonded to carbon. So in other words, this double bond would be replaced by two oxygens like this for determining the priority of different groups. Similarly, oxygen would be considered to be bonded to two carbon. Let me give you an example here so that you understand it better. And I'm going to show you how to do problem number 3.41C. question is rank the following substituents according to the sequence rules or priority rules. So they first gave you CH3. These are all substituent groups attached to the double bonded compound. Then you have C double bond OOH. I'm going to write down a structure like this by considering 4 bonds around carbon, 2 bonds around oxygen. That makes it a lot easier to think about this problem. CH2, then OH, OH, and the last one is CH double bond O. CH double bond O. So I need to assign priorities to this, and I'm going to identify the lowest priority and go towards the highest. Now here, in each case, there's carbon, so you can't make a decision. Then you need to go to the next bonded atom. This one has bonded atom, which is only hydrogen. So obviously this has the lowest priority. So let's have lowest would be CH3. Now let's look for the next higher one. Each of these compounds are bonded to oxygen. Like if you think about this, this is bonded to oxygen, this is also bonded to oxygen. So you cannot just make a decision based on that. We need to go to the next bonded atom. This compound has next bonded atom hydrogen. On the other hand, others have oxygen. So obviously this would be the next priority next to methyl group. So I'm going to write down here CH2OH. Now I have 2 more substitution groups left, which is this one and this one. Remember, this is a double bonded oxygen. So as if you consider that the carbon has 3 bonds with oxygen, 2 bonds are coming from here and 1 bond is coming from here. So that's the 3rd bond. Here, for this last substitution group, you'll be counting as if there are 2 bonds, CO bond. So this has 2 CO bonds and this one has 3 CO bonds. So obviously this would have higher priority than this. So my next priority level would be this, CHO, and the highest priority group is going to be COOH. So keep in mind this is lowest. I should specify this so that you don't get confused. Lowest, and this is highest priority. This is a homework problem 3.31 where you need to draw E3-methyl hept 3N. First I would forget about E or Z. I would just focus on drawing this structure, and I would begin with the N part, hept 3N. So basically it's heptene. 3 is the location of the double bond. So let's first write down 7 carbon, because hepta means 7, 2, 3, 4, 5, 6, 7. Let's assign numbers on the top. 1, 2, 3, 4, 5, 6, 7. It doesn't really matter from which end you start numbering 1. Now key thing is that the 3rd location you must have a double bond. So I have a double bond in here. In addition, in the 3rd location you have a methyl group. So that's methyl group. Now before you write down E or Z, you need to write down hydrogen around that double bonded carbon. Carbon 3 has 4 bonds, so you cannot attach any hydrogen. On the other hand, carbon 4 has 3 bonds, so obviously it can have 1 hydrogen. Now keep this in mind, carbon 3 or carbon 4 each has sp2 hybridization, because double bond for hybridization would be counted as a single bond or one pair of electron, as if there are 3 pairs of electrons around carbon 3 or carbon 4. Now sp2 goes with 120-degree angle. Now let's draw it properly to reflect that kind of angle, because that would be helpful in determining before you draw E or Z. So let's write down carbon-carbon double bond. Okay. Now I'm going to focus on these groups which are bonded to carbon-carbon double bond, because they are going to determine E or Z. Now let's change my color of the pen so that I can show you high priority and low priority, and H doesn't get, you don't get confused with H atom and high priority H. Now on the left hand side of this double bonded compound, carbon-carbon double bond, yep, this is high priority H, because there's 2 carbon there, and this carbon represents methyl group, gets the low priority. On the right hand side of this double bond, let's draw it more clearly, CCC gets the high priority, whereas H gets the low priority. H is hydrogen. Now keep something in mind. In order to be E, in order to have E, you must have high priority group on opposite end. So let's draw a line here so that we don't get confused. Now on the left hand side, I have CC as high priority, so I'm going to write down CC on the top. That would automatically place carbon, this carbon, on the bottom, because that's the 2 things that you have. Now let's hypothetically split the molecule. Now we are focusing on the right hand side. Since I have high priority group, which is CCC, and that, let's also write down here, this is the high priority H, this is the low priority L. Okay, now I have CCC. CCC. Again, I'm going to change the pen color for hydrogen. This is the hydrogen atom. Now I would have high priority on the top and the low priority on the bottom. Now you can see here I didn't draw the right structure, because the structure that I got is Z, 2 high priority on the same side. So what I'm going to do now, knowing the fact that I got Z, I'm just going to change these 2 groups, and that would automatically give me E. So this is the Z isomer, even though in question they don't ask for Z, but we have drawn it anyway. So let's now redraw it so that you're going to get E. So I'm just going to change position of these 2 groups to be C double bond C. Now I'm going to keep it intact. CC would be intact. Let's draw a line here, and this is C here. And remember, I'm going to switch, so C would be at the bottom and H should be on the top. So make sure that I copied everything right. So this is the high priority group, this is the other high priority group, and high priority group, and they're on opposite side, so we got E. So this is the answer you'll be looking at. You can, when you get experience, you can quickly write down the right structure right away rather than going through E or Z. I've shown you that mistakenly if you get Z, you can quickly change it back to E just by switching 2 of those, substitution 2 of the groups on one side of carbon-carbon double bond. So this is our intended structure, which is E3-methyl hept 3-ene. Here we're going to discuss four types of organic reactions: addition reaction, elimination reaction, substitution reaction, and rearrangement reaction. The first example that you see here is an addition reaction in which hydrogen is added to double bonded carbon. So one hydrogen is added here, the other hydrogen is added here, and that's how you end up with CH3CH3. So addition reaction normally takes place to double bonded or triple bonded compound because they have unsaturation. It doesn't have to be just H2, it could be Cl2, Br2, I2. Those could be addition reactions, or it could be just HCl, HBr, HI, where hydrogen goes to one carbon, Br goes to the other one. The second reaction that we're showing you here is an elimination reaction. Why is an elimination reaction? If you look at carefully the reactant and the product, you see that reactant side there was no double bond to begin with. The product side, you see that there is a double bond. Now, how did you get that double bond? One hydrogen and Cl were eliminated and forming a double bond, because when you get rid of this H and Cl, then the carbon and carbon makes the second bond, and which is the double bond, and then HCl. So in elimination reaction, mostly you get unsaturated compound from a saturated compound. Saturated means alkanes or alkyl halides. So in this case, unsaturated compound is a double bonded carbon compound. It can also be a triple bonded compound. Now the substitution reaction. In presence of light, Cl breaks down as the radicals. Cl and Cl, that's how it breaks down. The light breaks down this bond. And then with series of reactions, it eventually gets rid of this H, and Cl goes there, and it makes this compound, methyl chloride. So that's clearly a substitution reaction where Cl takes the place of hydrogen. Now next reaction is rearrangement reaction. Now if you look at carefully, these two methyl groups are on the same side of carbon-carbon double bond. So that's cis, and there are only two groups attached to two of those carbons. So cis trans isomers are possible, but this one is cis. So it's called cis but2-ene. Why but? Because the longest chain in naming a compound, that's what you're going to use, has 4 carbon, and that's why it's butene. And in the second position, you have the double bond. In presence of an acid, it rearranges into trans isomer. This is methyl is one side, this is completely on the opposite side. So trans but2-ene. So this kind of reaction is called rearrangement reaction, because here methyl groups are reorganized from cis to trans. Now we're going to go over problem number 11. It's coming from page 90. This would be a good problem to go over, and that would give you an idea what reaction type would be addition, elimination, or substitution reaction. So let me first write down the question. CH3 Br plus KOH. The product is CH3OH plus KBr. We're supposed to identify the reaction type in this case. If you examine the reactant side, you have CH3Br. On the product side, there is no Br, rather there is OH. So clearly you can see that OH is displaced Br. So obviously it's not an addition reaction, it's not an elimination reaction, rather it's a substitution reaction. So I'm going to write down here substitution. Now let's go over part B. CH3CH2Cl, that's the first compound. CH3CH2Cl plus NaOH and this gives CH2 double bond CH2 plus NaCl. Now the question is, what kind of reaction is this? First thing we notice that, again, by examining this reactant and product, especially these two, you see that this Cl is gone. Together with that, there's one of the hydrogen is gone from here. And we didn't have any double bond in this compound. If you write down those the structure of CH3CH2Cl, you'd find that there is no double bond or triple bond in this compound. But the product has a double bond. With the elimination of a hydrogen from this carbon and Cl coming from this carbon. And that's elimination reaction. So two elements are eliminated in this case, resulting in a double bond or unsaturation. So elimination reaction normally results in a double bond or a triple bonded compound. So this is an example of elimination reaction. Now part C, you're going to write down CH2 double bond CH2 plus H2. This gives CH3 CH3. Again, here you can see that you started with an unsaturated compound with a double bond, but you ended up with CH3 CH3, no double bond there. So what is happening here? One hydrogen is added here, the other hydrogen is added here. So that's purely an addition reaction. Reaction mechanism tells us how a reaction takes place. Often reactions happen due to the presence of certain species like free radicals or sometimes ions, so mechanism could be different. In this simple case of hydrogen, H2 molecule, now if I use some kind of radiation, then a hydrogen molecule would break down into hydrogen free radical. So these are neutral hydrogen, and each can cause a certain type of reaction. This is homolytic, that means it breaks down evenly so that each atom takes one electron. Heterolytic is unsymmetrical cleavage. That means one hydrogen becomes +1 and it doesn't have any electron. The other hydrogen gets both the electrons and gets minus. And that's unsymmetric cleavage that results in H+ and H-. We need to understand what is nucleophile and what is electrophile. Nucleophile means nucleus loving or positive charge loving. So it must be rich in electrons or carry a negative charge. Electrophile, on the other hand, is electron loving group, which is usually positively charged or deficient in electrons. In a mechanism, flow of electrons happen from one center to another, depending upon who has extra pairs of electrons, can often donate its electron pair to the atom which is positively charged or has some partial charge development in case of a polar bond. In this particular case, this carbon is delta plus, has a slight positive charge. Br is delta minus because Br is more electronegative. So obviously the reaction happens like this. Electron pair from OH minus is attracted to that positive end of this carbon. Temporarily there'll be 5 bonds because this OH should be there, but as we know that carbon cannot have more than 4 bonds, so it has to give up this bond. And that's why Br gets separated as Br minus, and we get this compound, which is called an alcohol. Now, obviously, you may have this question in mind, why Br leaves? Why not hydrogen? We call it leaving group. Halogens are very good leaving group. On the other hand, hydrogen is not. What that means is in a reaction, Br, Cl, I often would leave as their anions, but hydrogen is not like that. It would like to stick to that central atom. Now here we are looking at a mechanism of reaction of an alkene with HCl. Now in this structure you are seeing that the double bond, the electron pair of double bond is contributed to H plus of HCl, and that's how it gets to this carbocation, the next carbocation, after attaching this hydrogen, and then Cl minus is attracted to this carbon plus, and then it gives the final compound with Cl bonded in here. I'm hoping that you'd be able to understand that this carbon gets positive charge because that has 3 bonds, and obviously 3 bonds means if you consider the shared electron pair, it would get the share of 3 electrons. And carbon has 4 valence electrons. Now in this compound it has 3 for this carbon, so that means it lost 1 in the sharing, so that is plus 1. In previous chemistry courses, you learned that reaction can happen both ways. That means reactants can give you products, at the same time also products can break down into reactants. That's why you have double arrow here. This is a very popular inorganic reaction, but organic reactions are similar to this. You can get products, but products can also break down into reactants. We're going to explain this whole phenomenon on the basis of what we call transition state and reaction intermediate. I also want to remind you what is exothermic reaction and what is endothermic reaction. Exothermic reaction, heat is given off. In other words, if you have put a thermometer in there, temperature would go up. On the other hand, in endothermic reaction, heat is absorbed. So you'd see a cooling effect and temperature would go down. In this slide, we're showing you how a reaction takes place between CH2CH2 and HCl in order to give you a product which is CH3CH2Cl. Every molecule has its electron cloud. That means electrons surround them, so there are lots of those electrons. HCl also has that. In order to make a bond in a chemical reaction, these molecules will have to be close to each other. But as they get close, those electron clouds repel each other. In other words, they need to have some extra energy so that they can come close to each other. And as there is a progress of reaction and as these molecules come closer, you can see that its energy is increased because they need to gain that extra energy, and it goes to the top of this energy barrier, and we call this, the top of this energy barrier is called transition state. Now from transition state, it can go back to the reactant or it can form the product. Often before it forms product, there's an intermediate formation. In many reactions, this happens, like in this case, CH2CH2, that molecule gives a carbocation as an intermediate, and then carbocation intermediate finally forms the product. There is a small energy barrier. Now this is comparable to the case, assuming that you have your home on this side of the hill, and your mom's home is on the other side, on this side. In order to go to your mom's house, you need to go to the top of the hill and then go to the other side. If you change your mind, you can also slide back to your house. Often it happens that before you go to your mom's house, you take a stop over at your uncle's house in between. And that's like reaction intermediate. From uncle's house, after you take rest, then if you want to go to your mom's house, again, there is another hill. There's a small hill there. And then you go to the top of that hill. That's called second transition state. And then can go to the right-hand side of your destination. So basically, in an organic reaction, you would have reactants, transition state. In some cases, there is an intermediate, and that intermediate finally forms products.